Hey, it's Jim, and this is level 1 of the CFA program, the topic on quantitative methods, and the learning module on Introduction to Linear Regression. This is part 2. Let me caution you, if you've stumbled upon part 2 before watching part 1, go back and watch part 1 first, and you'll see that we covered the fundamental relationship between the dependent and the independent variable. We talked about some of the assumptions. Remember how I emphasized this concept of a least squares criterion. We're going to move on to essentially some hypothesis testing here on the coefficients that are produced by the regression model. We'll talk about the intercept, we'll talk about the slope coefficient, then we'll move on to an analysis of variance, and then we'll end with a brief discussion on some different functional forms. So let's get right to it. Hypothesis tests of the regression coefficients. Let me go ahead and start with an example. Let's suppose that we are trying to determine if there is a relationship between changes in dividends and stock price. So let's suppose that we go out and collect a sample of 50 or 100 different companies, and we isolate a decision by the board of directors in which the dividend is changed, whether it's increased or decreased. Some of them will be 2% and 5% and 10%. Some of them will be minus 2% and minus 6% and minus 50%. Then let's collect data on the stock price reaction. And let's just take this really simple. Suppose we go 1 week before the dividend change announcement and 1 week after the dividend change announcement. So we collect all this data. So what are we interested in? We're interested in asking ourselves the question, hey, if dividend changes increase, in other words, if the board increases the dividend, does stock price increase? I mean, that makes perfect sense based on all the material that we're covering inside of the CFA program. So what we do is we run a regression model and we come up with some results, just like we did back in part 1. We'll have an intercept term and we'll have a slope coefficient. So what we're going to do now is test the significance of that slope coefficient. So let's go back to my example. Suppose in some crazy world that every time the dividend increases and every time the dividend decreases, the stock price before and after that announcement change stays the same. Well, that's our null hypothesis. We're going to test that the slope coefficient, that B1, is equal to 0. So think about what that means. If we have changes in dividends on the horizontal axis, and we have stock price reaction on the vertical axis, well, what that means is that we're going to have a horizontal line somewhere in the middle of our graph. So that's our null hypothesis. We want to test that the slope coefficient is equal to 0. Now, what does that mean? That means that regardless of what dividends do, that the stock price stays the same. So you get the sense of what this null hypothesis is really asking us to do. So there it is in the blue box. Null hypothesis is that the slope coefficient is 0, which means there is no sensitivity. Remember I said to you that slope coefficient measures sensitivity. There is no sensitivity of stock prices to changes in dividends. And then the alternative hypothesis, here we have a not equal sign, so this is a two-tailed test, that it's not equal to 0 because we're allowing this particular test to be upward sloping or downward sloping. What do we think? I mean, we think that when companies change their dividend, if they increase their dividend, then stock price is going to increase. If they decrease their dividend, then stock price is going to decrease. So there we go. We state the hypothesis, but let's not be limited with a two-tailed test. We can have a one-tailed test. We could say something like, you know what, we think the slope coefficient is going to be less than 0. Or we could say the slope coefficient is going to be less than 5 or 10 or 0.65. I mean, we could pick almost any number as it relates to, whatever kind of an economic model that we're testing. A really cool test is to collect a sample of firms take a look at their weekly stock returns, take a look at the weekly stock returns for the S&P 500 index, and that slope coefficient in a simple linear regression is going to be the beta, the measure of systematic risk for that particular stock. So you could test that the beta is equal to 0, but that's probably not too useful. But we might want to test whether the beta is equal to 1. Systematic risk of our portfolio of stocks is equal to the market portfolio of stocks. So typical hypotheses can be almost anything. So don't be intimidated on the exam if you get what looks like some kind of a crazy null hypothesis. It means that the researcher has this idea somewhere embedded in the fundamental and underlying economics, and he or she wants to test that kind of a model. We'll go ahead and identify the appropriate test statistic. Remember, in a previous recording, we had a really cool slide where down the left-hand column, we had all of the different possible tests and when they're going to be used, like a t-test and a z-test and a chi-square test. Well, the test for measuring the significance of a slope coefficient is the t-test. Now, I'm really curious as to why the reading emphasizes the F-statistic here. And it is an appropriate test, but the F-stat tests whether the individual slope coefficient is different from 0. But the t-test, let me go back here quickly, that could be that we're testing that the slope coefficient is equal to 0, or it could be less than 1 or greater than 55 or whatever it is. So remember that the f-test is dialed in to the slope coefficient being different from 0. The t-test, when it is used like it is back here in that first HO, beta 1 is equal to 0, then it's going to be a t-test. So there is the test statistic. All we're going to do is take the beta 1 hat, which is our point estimate from the regression model, minus the hypothesized slope coefficient. So back here in this first one, that's going to be 0, but it could be 5 or 10 or whatever those numbers. And then we divide by the standard error of the slope coefficient. And then here, k is 1, because we have one independent variable. So the test statistic has 2 degrees of freedom, n minus 1 minus 1. Now, this standard error of the slope coefficient, here's the equation. You remember what I said to you back in part 1 is that, boy, there are tons and tons of these formulas that look fairly cumbersome and difficult to memorize. And I said to you, you know what? It's probably a good idea to memorize these things, but I'm going to give you a shortcut. And the Institute is probably going to give you a shortcut because this can be summarized in a table. Now, this one here you may have to calculate, so this is always a good one to memorize. Level of significance, for some reason, all stats professors will say something like, you know what, the standard level of significance is 5% because we like to make some conclusions with 95% certainty. That leaves just a 5% chance that you're going to be wrong. But the alpha, which is a measure of this level of significance, it could be 1%, it could be 0.5%, it could be 3%, although I don't think I've ever really seen a 2 or a 3 or a 4. There's nothing interesting about 5. It just happens to be, 95%. People like to be 95% confident in something. Rarely have I seen 10%, and I've never seen 20% or 50% or 80%. I mean, think about it. If you want to say something like, you know what, our level of significance is 75%, that means that you don't care if you're wrong. So 5% is pretty much a standard, but make sure that you read that alpha in the question stem, because I know that stats professors, and I'm guessing the Institute, they might throw a 1%er in there as well. State the decision rule. We've done this a bunch of times in previous learning modules. So all we're going to do is compute that test statistic and then compare it to a value on the table. That value on the table is known as the critical value, and we're just going to compare the two. And if you think of a bell-shaped curve, if that if that critical value falls, if the test statistic falls somewhere in the middle, like in the meat of the curve, well, then that means something. If it falls on the edges, that we call those the tails, then it means something else. And the tails, that probably means we're going to reject. So then we're going to calculate that test statistic and then make the decision. So here's another good reason why I'm referring you back to part 1. Here is a summary of the table that we used throughout part 1. And notice that the Institute is probably going to give you this table. They're probably not going to give you the unemployment rate and the inflation rate and then ask you to compute all of those other individual values inside of the rows and columns. But remember what I said to you back in part 1 is that the important thing is what we have bolded at the bottom. The summation terms of things like, hey, how much of the variability in the dependent variable is explained, that's the key word there, is explained by the variability in the independent variable. Well, notice at the top there, we're just repeating what we said in part 1. There's variation explained, variation unexplained, variation. So you see how this works, is that the ratio of explanation and unexplanation is super important. So in the blue down at the bottom, there is the regression model, 7 minus 0.9, plus there's that error term out there. So we need to test whether that slope coefficient is positive. Ooh, that's critical there at the 5% significance level. So look at the slope coefficient. It's a minus 0.9. We want to test whether it is positive. We could test whether it is negative. We could test whether it equals 0. We could test whether it equals a -1 or a +1 or a -10. But here, for some reason, we're interested in knowing whether this is an upward slope, which means a positive relationship, or a downward slope. So let's go ahead and put together that null hypothesis. There it is. Beta 1 is less than 0 versus the alternative hypothesis. There's our calculated test statistic, and what we're going to do is we're going to go ahead and use our equation to go ahead and compute that denominator, right? That standard error. Let's go back here. Where was I? Let's go back right there. We're going to calculate that standard error of the slope coefficient. But remember what I said back in part 1, most of this stuff can be obtained from the table. So notice what we're going to do. That standard error, it's nothing more than, well, there's the number, 3.136 divided by 8. Well, there's the degrees of freedom because, yeah, what was that? We had 10 years, right? So 10 minus 2 is 8, right? I don't think, we didn't know that that was 10. I guess we knew the dots in there. We could go ahead and count on our fingers. And then, so there's that 3.136. So let's go back here. Where's the 3. Oh, there we go. There it is. Boy, the variation unexplained. So remember that sum of that column is going to help you compute the denominator in the test statistic. Then we can use that to compute the standard error of the slope coefficient there, right? S sub B1. So there's the 1737. And then we go ahead and calculate the test statistic. So there we go, minus 0.9 over the 1737. We're going to subtract 0. There's the 5.19. We get out the table, which we give you here on the slide. So run your finger down to degrees of freedom of 8. Run your finger over to 5%, because this is a one-tailed test, right? So you get the 1.86. So minus, you got to do this on the minus sign because we're doing less than, right? That's our null hypothesis. So we fail to reject the null hypothesis, and we conclude that the estimated slope coefficient is not positive. Let me just go back real quickly to what I said in part 1. Look, in kindergarten, we can look at that minus 0.90 and we can say to our kindergarten teacher, yes, that has a minus sign in front of it, so therefore it is negative. But that's not sufficient inside of our quantitative methods and our statistical analysis. We need to ask ourselves the question, is that minus 0.9, is it statistically negative? And so, yeah, we come up with a failure to reject that null, which means we accept the alternative hypothesis. Now, there's a very interesting section inside of this learning module, and I think these are great exam questions, but I'm not quite sure that the Institute would go so far as to show you this or test you on this, because this is really a stats phenomenon or a stats result. So let's go back to our learning module when we had that conversation on testing correlation coefficient. Remember I think there was a learning module called parametric and non-parametric tests, and that whole learning module was on tests of correlation. So in the blue box, that test statistic should be familiar to you. We're going to test the hypothesis, the null hypothesis of whether the correlation coefficient is equal to 0. Once again, there are n minus 2 degrees of freedom. So, boy, that should be in your memory bank. Well, let's go ahead and compare what we just did versus what we did in a previous learning module. So there is the test statistic for correlation in the upper gray box. Now, look at the second teardrop point. We needed to know what the correlation coefficient between unemployment rates and inflation is. I don't think we knew that back in part 1, but there it is, 0.8782, and it's minus. So if we do all that for the test statistic, we get around 5.2, minus sign, right? Well, that's exactly what we just calculated in, where do we do this? We just calculated there. It's about minus 5.2. So you see the relationship that exists between correlation testing and the linear regression model, right? Correlation doesn't mean causation. We said that back in that previous recording. But what we do when we make this statistical test is that we rely on the t-distribution, and you can see that that's true for both of these statistical tests. Now, of course, the correlation test is just a test of whether or not the correlation coefficient is significant. The linear regression test statistic, the t-test in linear regression, is a much more sophisticated kind of a model with all of those assumptions that we discussed back in part 1. But the cool mathematical, or at least statistical, result is that these two test statistics are going to be the same. Let me go ahead and just repeat what I said a few moments ago. I'm not quite sure how the Institute could come up with a legitimate question showing these two, but your current knowledge base of understanding the relationship between correlation and linear regression, that has to add some value to your preparation for the exam. All right, what did we just do? We just did testing the slope coefficient significance. Now let's do the intercept coefficient. And so the equation is exactly the same right there in the blue box, but instead of B1s in the numerator and standard deviation of B1 in the denominator, we just switch it over to the intercept term. But we need another formula for the standard error of the intercept, and there it is at the bottom. So once again, we have this table, and we're comparing the relationship between inflation and unemployment, just like we did previously, just like we did back in part 1. There's the regression model in blue box down at the bottom. So we want to test whether the intercept term is greater than 1 at the 5% level of significance. There's 5% again. Could be 1%, could be 2%, could be whatever. So here's 5%. Back in kindergarten, we see that 7.1. We see that number is greater than 1. So the kindergartner in ourselves is saying, wait a minute, of course, 7.1 is greater than 1. Why do we have to do the rest of this test? But our now CFA core to ourselves says, well, while on the surface it might look like it's greater than 1, we need to prove statistically that it is. So there we go. We'll do the hypothesis. We'll do the test statistic. We'll go ahead and calculate those extra standard deviations there, 2.8, and there's the t-stat. So there's our degrees of freedom. I think that's the same thing as it was before, 1.81. So we're going to reject the null hypothesis and say that the intercept term is greater than 1. So here we are. Statistics agrees with our kindergarten sensitivities or sensibilities. So far in part 1 and part 2, And in many of the regression analyses that you're likely to see on the exam, the data that is collected is easily identifiable as quantitative data. In other words, in my example, what did we have? We had changes in dividends, right? 3%, 4%, minus 5%. We had changes in stock price, right? 44 to 44 or 80 to 80 in my silly example, or 44 to 85, right? You could see those, and those were mathematical numbers. So we have this quantitative data. But what happens if we don't have quantitative data? Well, that's where we use these things that are called dummy variables. And that term dummy variable goes way, way back to when these were created. But in recent years, different names have been attached to it. You can see there up at the top, indicator variables or binary variables. Binary just simply means that there are only two choices. And the two choices are either 1 or 0. The obvious example is that, it's either day or night, right? If you do something during the day, that's a 1. If you do something during the night, that's a 0. And so qualitative information somehow has to be transformed into something that looks like a quantitative data. So that's what this whole section in this learning module is about. How do we use these dummy variables? And I'm going to just continue to use that dummy variable because that's how I was taught, hundreds of years ago when I was back in graduate school. So look at the example that we have down here at the bottom. Let's suppose that we're trying to determine whether or not a stock, an individual stock, is part of an ESG-focused fund. So some stocks will be part of this fund and some stocks will not. Well, how do we quantify that relationship and the difference between those two stocks? Well, all we're going to do is say something like, hey, look, if the stock is part of an ESG-focused fund, we'll give it a value of 1. If it's not part of the ESG-focused fund, then we'll give it a value of 0. All right, so imagine what this looks like. Here, let me go back here quickly. So what did we have here? We had unemployment rates and we had inflation rates. Those were all quantitative variables. So now we're going to have, here, let me go back here. What are we having? We're having monthly returns. So imagine a column of monthly returns. And then the next column is going to be either a 1 or a 0. You see how we transformed qualitative data into something that we can use regression analysis to help us establish a relationship between the dependent variable and the independent variable. So there we go. In the light blue box at the bottom, there's what the regression model looks like. So let's suppose that we get out some software and here are the results. Well, we have an intercept term and we have a slope coefficient. We've got standard errors and we have calculated test statistics. Now, remember what I said to you, and I think I kind of glossed over this back in part 1, is that the test statistics there, right, they're close to 10. Well, assuming we do this for a bunch of firms, that's going to result in us rejecting the null hypothesis. Remember I said, kind of a loose definition was around 2.0. Well, in our previous example, what was it? It was 1.8 something. And then an example in part 1, I think it was maybe 2.1 something. So it's around 2. So just loosely, when you get to this table on an exam, look at that calculated test statistic. And if it's 9.5, well, you know that you've established a significant statistical relationship. Now, a couple of other interesting things about this dummy variable technique is that if you look at the second table down there, there's a mean and a variance. There's the 10 observations for focused stocks and 38 observations for non-focused stocks. So there are the means and there are the variances. Oh, so what I want you to do is I want you to look at the monthly returns of the non-ESG stocks. What's that number? 5468. Notice that that's the coefficient for the intercept term. Because of the way the mathematics works, when we're performing this least squares criterion, those two numbers are always going to be the same. Also, if you take the difference between the mean of the focus stocks and the mean of the non-focus stocks, what's that? 165 and 54. Look at that over there. You get 1.1052. Look back at the slope coefficient, 1.1052. So this shouldn't be a surprise for those of you who are mathematically inclined that if our independent variable is a 1 or a 0, then the means have to be related to the estimated coefficient. So I think that's a really cool exam question, the difference in the means. So think about it. If you have the top table as part of the question stem, the institute could say something like, hey, using this, what is the difference between the mean of the ESG focus fund and the non-ESG focus fund? Well, right, you're not going to be given that second or that lower table. Just go to the slope coefficient. Here's a kind of a summary observation of what I just said up there in the purple. There's the intercept and there's the slope coefficient. So let's move on to the hypothesis test. So we can test whether that slope coefficient is equal to almost anything. But in this case, we're going to test to see if it's equal to 0. So what is it there? It's 1.1052. Well, our kindergartner inside ourselves is saying, oh yeah, 1.1, that's not 0. But now we know we have to prove this statistically. Notice we have not equal sign in the in the alternative hypothesis. So this will be going to be a two-tailed test, degrees of freedom. What do we've got? We've got 10 on one side, we got 38 on the other side of observations. So that's 48. Take out the 2, right? N minus K minus 1. So that's 46. So you could go back to the table, which we don't provide you here, but you should have a t-table right beside yourself. Split the alpha in half, right? You got 2.5 on this side, 2.5 on this side of the normal distribution. So there's the critical value of 2.013. Boy, what did I just say to you earlier? It's going to be around 2. And so let's go back here. What was that test statistic? They were both around 9. So we're going to say, hey, yeah, we're going to reject the null hypothesis, and we're going to say, yes, we agree with our kindergarten self. Now, all this stuff that we've been doing with tests of the coefficient and in the dummy variable technique, we can summarize that with a p-value. And now we introduced this concept of the p-value back in part 1. But there, look at the first bullet point. This is taken from the learning module, but also it was repeated back in part 1. It's the smallest level of significance at which the null hypothesis is rejected. So if I go back here to this table, if we have that test statistic that's 0.99, right, for the slope coefficient, the p-value for this thing here, now what did we do? We rejected it at 5%. So the p-value here, it could be 4%, it could be 3%, it could be 2%, right? But it's essentially the smallest value at which the null is going to be rejected. So the fact that this is 9.95 means that the p-value for this thing right here is probably 0.0001 or something like that. So that example ought to really give you the idea. So look at that that indented bullet point. The smaller the p-value, the smaller the probability of rejecting a true null. So there's that type 1 error that we talked about. Remember, I gave you that great table in a previous learning module about the difference between type 1 and type 2 errors. In fact, I even think I asked you to take a picture of it. Yeah, most software packages will provide. So let me go back here real quick. So they'll give you this stuff here. Actually, let me go back here. They'll give you all this stuff here, right? And then they'll give you the p-value as well. So look for a p-value over on the far right column. It might be there on the exam. It might not be there, but you can kind of figure out what it's going to be based on the test statistic and how easily the null hypothesis is rejected. All right, let's move on to the analysis of variance. And the graph that we have here is a summary graph of what we did back in part 1. So let me just quickly remind you, over on the far right in the top corner, there's our regression equation. There's our red regression line. So in this case, this intercept term is somewhere down around that first slash point, whatever that number is. And the beta is positive, so we have an upward slope. What we're interested in this analysis of variance, some people call it the ANOVA table, is deciding how much of the variation in the dependent variable is explained by the variation in the independent variable. So notice we have, what is that, dark blue, and we have red, and we have orange, and so this is exactly what we had back in part 1. Let me go ahead and just remind you that over on the left-hand column, we have, the left-hand side of the graph, we have the total sum of squares. So that's the distance between the yi, right there, that each yi, and all the way down underneath most of the red line, and that's y bar. That's the mean of the dependent variable. That's total variation. And that has two components. Some of it can be explained, and that's the distance between the mean, y bar, and the red line, the red equation line, and the unexplained portion of it, which is the distance from the red line all the way up to each yi. So there's a blue box over there. We have done that in part 1. So the total variability has two components, the explained and the unexplained. And so look at that second diamond or arrow point. This is important here. So analysis of variance is used to determine the effectiveness of the independent variable in explaining the variation in that dependent variable, right? Suppose you come up with an analysis of variance and the conclusion is, you know what, Jim, your independent variable, it really stinks. It does no good. It explains no variability. How about this example? The number of times that Jim uses his John Deere tractor to cut his lawn during the summer months compared to the returns of Procter & Gamble on the floor of the New York Stock Exchange. Boy, if we're going to run a regression and then perform an analysis of variance on the relationship between Jim's lawn cutting and what goes on the floor of the New York Stock Exchange, what are we going to get? Well, we're going to get tons and tons of unexplained variation, maybe even 100% of unexplained variation. All right, what did I say earlier? What did I say in part 1 is that, of course, these things have huge equations, right? We've got summation signs. We're taking the difference between y variables that we predict, y variables that we observe, versus the mean of the y versus the predicted, and we're squaring them. So there's tons and tons of work. And think about this previous example. I mean, we had, what did we have back here? 48 observations. So imagine doing this on an exam and having to come up with this table. Well, of course, the Institute is not going to make you do all that, but it's going to summarize it. So how are we summarizing this? We're going to summarize it with an R squared. So look at the R squared. What is it? It's explained variation over total variation. What's the R squared of my model with lawn cutting and returns on the New York Stock Exchange? Probably close to 0%. So my advice back in part 1, and I'm going to continue to use that advice, is to, hey, look at these equations, work through the math like we did back in part 1, but focus on what's at the bottom and the far right of the table. Now, before I get to the next slide, I want you to look over there on the two final columns. We've got this mean square and we've got this F-Statistic. So this is super important. When the Institute asked you to compute the F-Stat, this is going to be the easiest thing that you've ever done on any kind of exam dating back to kindergarten. So look at what that mean square is. Look over, scooch all the way over to the first column. Notice in parentheses we have explained versus unexplained. So that's what those mean squares do. And that F-Stat is just a ratio of those two. All right, so let's go ahead and look at a quick example here. Here's an analysis of variance table from that inflation rate and that unemployment rate that we did back in part 1 and today. So there we go. Regression, error, total, 10, 3, and 13, right? So those were all part of what we did before. There are the degrees of freedom, and there are the mean sum of the squares. notice to get that mean sum of square, all we have to do is say 10.568 divided by 1. That's where we get the 10.568 for the mean sum of squares. And then for the mean sum for the errors, we take the 3.136 divided by the 8 and gives us the 0.392. So what do we say in that, in one of those slides, software packages give you a whole bunch of output stuff. Well, here's all the output stuff. Do you really need to know all of these equations? Well, the professor in me says absolutely. The test creator and the let's make sure we get the correct answer, I'm going to still say yes, make sure you know those equations, but look at how easy that is to get the mean sum of the squares for the regression, the mean sum of the squares for the error, and then the F-statistic. All right, so our test is, do we want to test the hypothesis that the slope coefficient is 0 at the 5% level of significance? Now we can do this with a t-test, but the learning module is emphasizing that we can also do this with an F-test. All right, so over in that far right column, the F-statistic is going to be the easiest calculation that you have made since kindergarten. All right, so let's go ahead and use our results from the table. We're going to take that mean sum of squares for the regression, put that in the numerator. We're going to take the mean sum of squares for the error term, put that in the denominator. So think about it. The Institute, they're going to give you this table. They're going to give you the 1056 and the 392, or they're going to give you that big table that we just looked at, and the one all the way back from part 1, and all you're going to do is divide to get the F-stat. So there we go, 10 divided by almost 4, so there's 26.96. Look this number up on the table. So we have, remember it's the F table, so we've got two degrees of freedom. So there's one independent variable. So we go to the 1, run our finger down to, what was it, 10 observations. So 10 minus 2 is 8. So what do you get there? 5.32. So there's the critical value. This is a one-tailed test, so we're using 5%. So what are we saying? 26 is greater than 5.32. So we're going to go ahead and reject the null hypothesis, and we're going to say that, well, let me go back here, that slope coefficient, what's our slope coefficient? That it is greater than 0. Now, a couple of interesting things here. I want to call your attention to our bottom bullet point there. The F-test duplicates the t-test for a linear regression with one independent variable. This is what we're going to see as we go through the CFA program, that when you have a simple linear regression, you don't have to do both F and T. And the reason for that is, well, look up at the orange arrow point, that the 2.306, if you square that, which we got from our previous slope coefficient test, you get 5.32. So statistically, these things result in the same conclusion. However, the Institute emphasizes F-test, so make sure you can do both here for simple linear regression. We're going to do F-test when we get to multiple regression in level 2, where we have multiple independent variables, and then the F-test is going to be super, super important for us. All right, moving on here to near the end of this learning module, what we're asked to do then is to use the model, right? So we have this model, we've collected the data, we have a regression output, we've performed an analysis of variance, and so we've made a conclusion that sounds like, you know what, this model's pretty good. The R-square is 91%. Both the intercept and the slope coefficient are statistically significant, so we like this model. Well, let's go ahead and use it to predict the future. So this is called a predicted value. And so all we're going to do is say something like, hey, let's throw a value in for X. Use the results of the model to predict a value for Y. So here's our big old table from part 1. Unemployment rates, inflation rates. There in the red box is our estimated regression model. So let's go ahead and ask ourselves the super easy question. Let's suppose that we believe that the unemployment rate is going to be 4.5%. all we're going to do is take that 4.5% and throw it into the model. There we go. And we're going to say something like the predicted value for the rate of inflation is 3.053%. This seems to me like a standard stats question that my quantitative professors ask at my institution. This sounds like a great exam question for you guys in preparing for your level 1 exam. So know how to do that. I mean, this is super easy stuff. Then the next question is, okay, suppose we predict that 3.053%. How confident are we in that prediction? So we're going to come up with what's known as a confidence interval for the predicted value, which is also known as a prediction interval. So back here, we said something like, hey, we expect inflation to be 3.053, but then we want a range. What's the range? I mean, if I say, I think inflation is going to be 3.053%, and you say, okay, Jim, what's the minimum and what's the maximum? And I say, oh, the minimum is a minus 84% and the maximum is a plus 127%. You're going to look at me and say, you know what, Jim, your prediction is worthless. So we want to know what that range is, and that's all a predicted interval does for us. So we take the y hat plus or minus, right? We're going to add and we're going to subtract, and then we're going to use a critical value and we're going to use the standard error of the forecast. So we've been using these, I always like to say the word standard deviation. So the standard deviation of all of these things that we have been done, whether it's the slope coefficient or the intercept term or of the regression model, we're calling it standard error of the forecast here because it's a prediction interval. Now, we need to know that variance of the prediction error. Once again, there's a great old formula for you to know. But notice down at the bottom, boy, we think that it's unlikely that you'll be asked to calculate that. So it'll probably be given to you in the question stem, but there it is for you if you're asked for it. So here's an analysis of variance. There is the intercept term. There is our slope coefficient. This is stuff that we've seen in tables before, but we present it to you like this because this is about likely that the Institute is going to show you in the question stem something that looks like this. However, I caution you that they'll probably delete some of the answers inside some of the squares. Like, for example, they'll probably give you the top, right? R square, standard error, and the observations 10. And then degrees of freedom. You know what? If you know it's 10 and you know it's one independent variable, you should be able to get those degrees of freedom. 1 and 8 and 9, okay? Then they'll probably give you the sum squares column. They'll probably give you the mean square, though they don't have to. Remember, you can just do the 10 divided by 1 and the 3 divided by 8, but they're not going to give you the F in that far column, the 26.95, which we calculated, what was that, 4 or 5 slides ago. So then down below, there you go. You'll get the intercept. You'll get the standard deviation. You might not get those test statistics, right? So all you need to do is take 7.112 divided by 940. And the same thing for the unemployment rate. Those p-values over there, those will probably be given to you. And remember what I said earlier? What was that t-stat for that dummy variable? It was 9.9 or something, and I said the p-value was probably 0.0001 or something. Well, there's evidence that clearly I was estimating what it was earlier, but there's evidence that I wasn't too far off. All right, so let's do a confidence interval of that predicted rate of inflation of 4.5%. All right, so we need to go ahead. There's our repeat of the 3.053%, but now let's go ahead and compute these standard error of the forecast using that equation. So once again, we would need to go back to that original table. So, think about what the Institute is going to have to give you. They'd have to give you this table here, but then they'd have to give you this table here for you to do all of that stuff. So I think it's likely that you'll be given either the 45 down there at the bottom or the 6708. I mean, if they give you the 45, just take the square root, and that's probably okay. So you can get this critical value, 2.306, from the table. So just run your finger over and down, just like we did before. So here is the prediction interval. We'll start with 3.053 rate of inflation, right? That's our predicted number. And then we're going to plus or minus, we're going to add 2.306 times that 67, right? We got that right back there at the bottom. And then we're going to subtract it. So there's our prediction interval. So what did I say earlier? I said, hey, I predict 3.053% inflation. And you say, what's your minimum and your maximum? And I say, I forget the numbers I said, minus something and a positive. And you say, Jim, that's worthless. Well, now think about what we're saying. At the 95% level of confidence, we can be certain that our prediction is going to fall between 1.5 and 4.6. Do you see how this works? We're interested in using our regression model to predict inflation. And then we're interested in asking a follow-up question. All right, what's a minimum and a maximum? Now, wait a minute. Don't tell your stats professors that I said that. That 1.5 is not the minimum, 4.6 is not the maximum, but it's the minimum and the maximum according to our selected 95% level of confidence. If we did a 1% alpha, it would be a little wider. If we picked a 10% alpha, then it would be a little more narrow. I'm hoping that I explained that well enough for you guys. All right, this final LOS asks us to evaluate the relationship between a dependent variable and an independent variable if one or both of those variables are not linear. Remember in part 1, we talked about the assumptions of the simple linear regression model, that there is a linear relationship. Well, we have done this in a previous learning module in which we said, you know what, some variables are nearly linear. Maybe they take a log linear form. Maybe the logarithm of a model of a variable can be transformed into linearity. And so this last section in the learning module is really just a way of saying, it's not perfectly linear, but it's nearly linear. So let's go ahead and let's take the log of the dependent variable. There's number 1, the log linear model. So we take the log of y, but we leave x in its current form. Or we could do the Lin-Log model. There's number 2. We could leave y variable in its current form, but take the log of the x variable, the independent variable. Or we could do the log of both the left-hand side and the right-hand side. So the question that I think is very likely on the exam is twofold. The institute could give you, here, let me go back here, one of these 3 models, and let me go back here, give you an output like this, and the interpretation of the output is the same. So that's the first question. The second question is, well, which one of these models is better? So the institute could say, look, here's 1, here's 2, here's 3. And they could say, here's an R-squared, there's an F-test, and there's a standard error of the estimate. So look at the 1, 2, and 3 here. This is going to give you an answer on one of the questions on the exam. So if you're choosing from among those 3 models, pick the one that has the highest R-squared, pick the one that has the highest F-stat, pick the one that has the lowest standard error of the estimate. And knowing those 3 things will help you answer that one question on the exam. Now, the other question on the exam is, let's go ahead, here, let me go back here. Let's use Let's use the prediction interval model there in blue, and let's use one of these 3 forms. So make sure if you're predicting, you take the log of either the y or the x before you make your prediction. And that takes us through all of our LOSs. What I want you to do now is I want you to go and spend, I'm going to say 60 minutes on the problems at the end of this learning module. There's a whole bunch of really, really great questions. 38 or 42 of these questions back there. We've covered, I've been through those 40 some questions. We've covered everything that's in there. So you ought to be able to work through all of those questions. And since there are so many of them, I'm okay if you do this. I'm okay if you work through the questions that you know. Do this in order. If you don't know how to do it, go and look at the answer and then say, oh yeah, I get this. All right. And so go through all those 40 or some questions, and then I want you to go back and do it without any help from the answer key. So go through them 2 times, one with some help, one without help. So hey, thanks for watching. Have a great day and good luck studying.